Alright, here's a little video about titration, sort of revisit some of the things that we talked about in class. Hopefully you understand titration. You take a solution of a known concentration, which you call the titrant, and that's added to a known quantity of the analyte. And with that information, you can determine the concentration of the analyte. We are going to use this to basically determine the pH at any point along a titration. And that's generating those points are known as a titration curve. Alright, first thing, let's look at titration curve for a strong acid, strong base solutions, and the combination of the two produce a neutral salt and water. So if we look at a titration curve, we've got these points that go along and form this nice little curve like this. And we're going to look at this and think of it in four regions. Region number 1, region number 2, region number 3, and 4. So let's look and see what it is that is in the solution at any point. So thinking about point 1, initially, we're starting with a strong acid, and that's why the pH is so low, adding a strong base to it incrementally. Increasing the pH is why you see the pH increase as the volume of the titrant increases. So initially, starting at this first point, initially all that's present is acid, so strong acid. Then, in this region number 2, as we add base, what's going to be present is still strong acid plus a neutral salt. So the one thing that's going to determine what the pH is at any point in that region 2 is how much excess strong acid there is. In region number 3, at that we call the equivalence point, where the number of moles of the strong acid equals the number of moles of the strong base. And because that is a stoichiometric, they are stoichiometric quantities, then all of that acid and the base have been consumed to produce a neutral salt. And a neutral salt is just that. It's neutral, pH 7. And so region 3, the only thing that is present is the neutral salt. In region 4 here, after we have consumed all of the strong acid, so strong acid has been converted into the neutral salt, if we continue to add base, what's going to be left is just excess strong base. And so knowing the quantity of strong base in excess will allow us to determine the pH. And here in those four regions, directions for determining the pH at any step with a strong acid, strong base titration. The first region, you just take the negative log of the initial acid concentration. In region 2, you figure out how many moles of acid are in excess, divide that by the total volume, to be the volume of the acid initially plus the volume of the base that's been added, and that gives you the concentration of the excess acid, and take the negative log of that. In region 3, remember this is a strong acid, strong base, so it produces a neutral salt. So region 3, at the equivalence point, the pH is always going to be 7. And then in region 4, we're just looking at how much excess base is left, and so we determine the quantity of excess base, divide that by the total volume to get the molarity of the base, and then we take POH minus pH to get the pH. Wait, POH, excuse me, we take the PKW minus the POH, minus POH, and that gives you the pH. Alright, so this problem, sample problem, we're going to take 50 milliliters of 0.2 molar hydrochloric acid, titrate it, and we're going to titrate it with 0.30 molar sodium hydroxide. I want you to be able to calculate the pH after adding 20 milliliters of the base at the equivalence point and after adding 50 milliliters of the base. Now I'm going to work with the millimoles because that's just a little bit easier. So if you take the volume in milliliters and multiply it by the concentration in molarity, you get volume in milliliters, concentration in molarity, you get millimoles. And so starting out with 50 milliliters of 0.2 molar HCl, that means we're initially starting out with 10 millimoles of HCl. And then if we start and we add 20 milliliters of 0.30 molar sodium hydroxide, that means we have added 6 millimoles of sodium hydroxide. Now remember that this is HCl plus NaOH, and it produces salt, NaCl plus water. If we start out with 10 millimoles of that, and we add 6 millimoles of that, we're going to consume 6 millimoles of the HCl, consume 6 millimoles of the NaOH. We're going to produce 6 millimoles of NaCl. Now NaCl is a neutral salt, so what are we left with? We're left with 4 millimoles of hydrochloric acid, and that is going to be in a total of 70 milliliters. So that gives us a concentration of 0.0571 molar hydrochloric acid excess. And if we just take the negative log of that, you get pH equal to 1.24. Next spot, let's go ahead and calculate the pH at the equivalence point. Easy enough, strong acid plus strong base. At the equivalence point, pH equals 7. Now, can you determine the volume? I know it's not asked for, but let's determine the volume of NaCl, or excuse me, of sodium hydroxide required to reach the equivalence point. And that's easy. That's just stoichiometry. And so we could say we start with 50 milliliters of the HCl, and we multiply that by its concentration, 0.20 moles of HCl per liter. And we know that we are going to consume 1 mole of HCl for every 1 mole of NaOH. And our sodium hydroxide concentration is 0.30 moles of NaOH per 1 liter. And if we cancel out units, moles of HCl, moles of sodium hydroxide, liter, we're left with units of milliliters. And the volume of sodium hydroxide needed to reach equivalence point is 33.33 milliliters. Just a nice little bit of information. All right. Next slide, we want to calculate what is the pH after adding 50 milliliters of base. Now, note, remember we started out with 10 millimoles of HCl, 50 milliliters of base, that would be the volume in milliliters times concentration in molarity, gives you 15 millimoles of NaOH, and that NaOH will consume all the HCl, and you'll be left with 5 millimoles of NaOH. If we want to know the pH, we've got to take that 5 millimoles of NaOH, divide that by the total volume, which is 100 milliliters, and that should give us a concentration of 0.050 molar, and that's molar OH ions. And if we take pH is equal to 14, the pKw, minus the pOH, negative log of our concentration of OH, 0.050 molar, you come up with a pH of 12.70.